Starting from this video, we'll begin to talk about applications of complex numbers. And this particular one is about real integrals via complex methods. We already have a glimpse of that using residue theorem already. So it's just, the whole thing is like a continuum. So talking about real integrals via complex methods, right? First question is, why do we use complex methods in the first place? So first for integrals, I mean, from residue theory we did in the last video, you already see that, what would have cost you more time and more effort, you could use residue theorem to take care of some complex looking integrals. So some real integrals are difficult or impossible to evaluate using elementary calculus. That's one thing. So complex analysis provides tools such as contour integration and residue theorem. Now for contour integration, we remember that Cauchy's integral formula tells us that if you can confirm that the function is analytic, then its integral along a closed path is actually zero. So that makes that very easy. And for residue theorem, you can just apply that to actually, so all you just need is just multiply the sum of residues by 2 pi and you get your integral evaluated easily. So this allows us to evaluate integrals like minus infinity to infinity of dx over x squared plus 1 and integral from minus infinity to infinity of cos x over x squared plus 1 dx. So if you're going to do this normally in the real in calculus, this is going to be a lot of trouble, right? So it may not be impossible, but it's hard. It's harder if you, but thank God for residue theorem. So core idea here, we extend a real integral into the complex plane. So we have minus infinity to infinity of f of x dx. And we do that by considering integral along a particular path of for f of z dz. And then we apply the residue theorem, which simply tells us that the integral of f of z dz along a closed path is actually 2 pi I multiplied by the sum of the residues easily, and then we keep going. So of course in the last video we considered residue theorem, and here we are at it again. So if f of z has isolated singularities inside a contour, so this is a contour now, if you like, you can, that's what we've been calling C all this while, then the integral along the closed contour of for f of z dz is 2 pi I times the sum of the residues, and where the sum is over all poles inside the contour. So if you have 10 poles, you want to find the residue at each and every pole, and then you sum them up together, multiply by 2 pi I, and you get your integral easily done. All right. So the general strategy is to extend f of x to f of z. So you take it from the real domain to into the complex domain because it's functionally the same. And then you can choose a contour, then identify poles inside a contour, then you compute residues, you apply residue theorem, you show arc contribution vanishes, and extract the real integral. That's all. So example one, we can start with example one here. So for example one, right? Okay, I guess I need to show it in bits. So you want to evaluate integral from minus infinity to infinity of dx over x squared plus 1. I think we did this in the last video, by the way. So the complex extension of this thing will just be f of z equals 1 over z squared plus 1 right here. So z equals, so if you factorize this, that will be z plus 1 into z minus 1, meaning that you have z equals minus 1 and z equals I. So the poles at z equals I and z equals minus 1. So residues at z equals I, then, for residue at z equals I, which actually falls within the, which is in the upper plane, which we focus on. So z equals I now. So residue of f comma I will be limit as z approaches I for z minus I, this z minus I that gave us this z equals I, all over, uh, when you expand this, now you have z minus 1 into z plus z minus I into z plus I. So z minus I cancels z minus I. So you then have, so if you substitute z equals I, you have 1 I plus I, which is 2I. So the residue here is 1 over 2I, like that. So we don't bother about this one because this is not in the upper plane. It doesn't fall into the realm we're talking about. Okay, so we then apply residue theorem that integral from minus infinity to infinity of dx over x squared plus 1 is 2 pi I times the sum of residues. So 2I cancels 2I, so you just get pi, and that's it. So the final answer is pi. So if you do this in the real in real calculus, you have to start substituting. Maybe you say let x be tan theta, and you do long stories, and you still end up getting the same pi. So there's no point if you can actually use this residue. So Python verification, we do symbolic Python here, and we import sympy as sp, and we define x, we make x symbolic, and we want to find 1 over x squared plus 1. So we just say sp dot integrate. So if you integrate this, from minus sp minus from minus infinity to infinity, right? Infinity is given as minus sp dot 0 0 and sp dot 0 0. You end up getting pi. So, and this is not even complex, right? This is normal integration. So you end up getting the same pi. So residue theorem makes life pretty easy for us. So let's look at example 2 and see how that goes. So for example, 2 now, you want to evaluate I equals integral from minus infinity to infinity for e raised power ix over x squared plus 1 dx. So in the complex component of this will be every x becomes z. So f of z equals e raised power iz over z squared plus 1, right? So the residues, you get residues, two residues as usual, because if you factorize z squared plus 1, you get z minus 1 into z plus 1. So z minus 1 gives us pole z equals 1, and z plus 1 gives us pole z equals minus 1. But we focus on only pole z equals, uh, I mean, not 1, I rather. Z, z minus I gives us pole z equals I, and z plus I gives us pole z equals minus I. So residue at z equals I then becomes this. So you have residue. So limit as z approaches I. So a lot of that has been summed up here. But when I take the example later, you are going to get it better. So here now, we have once we just evaluate residue at z equals I. So that means that's the limit as z approaches I for e raised power iz over z squared plus I. So in that case, of course, and then you multiply by z. Okay, yeah, you factorize it. Okay, let me just do it. I think I've been trying to be lazy. Let me just do it and get it over with. So we have I to be, so want to evaluate I, which is integral from minus infinity to infinity of e raised power ix over z squared plus 1. I mean x squared rather, x squared plus x squared plus 1 dx. I think that's what we need to do, right? Yep. So what we just need to do is we turn it into a complex function. So as a complex function, we will have f of z equals, we have f of z, yeah, we have f of z equals e raised power iz over z squared plus I plus 1 rather. So z squared plus 1 can be factorized as z minus I into z plus I, because this is a complex thing. So the real deal is you have z squared equals z squared plus 1 equals 0. So that means z squared is equal to minus 1. So that's z equals plus or minus square root of minus 1. So z is plus or minus I. And that is why we can say that z is equal to I, or z is equal to minus I. So if you put it together, that's z minus I into z plus I is equal to 0. Okay? So that's how we get to factorize that in that way. So here now we have that z squared plus 1 is z minus I, z plus I. So we have poles, z minus I equals 0, and that implies that z is equal to I. And then we have z plus I equals 0. That implies that z is equal to minus I, like this. So, but this is the one in the upper plane. So we forget about this and we focus on this. So we need to now compute. So to compute to compute the residue, to compute the residue at z equals I. So what we then do is to say that residue of the function f at z equals I is to take the limit as z approaches I for what gave us z equals I. That's z minus 1, z minus I. So we have limit z minus I multiplied by the original, the function we have, this e raised power iz. So we have e raised power iz all over uh z squared plus I. I'm using that. That's the original function, right? But we know we have broken it down already. So that's limit as z approaches I for z minus I multiplied by e raised power iz all over z minus I into z plus I. Okay, so z minus I cancels z plus I. So we then have limit as z approaches I for e raised power iz all over z plus I. Okay, so you can then fix up the I. So we have e raised power I multiplied by I because z is I now. So e raised power I times I all over I plus I. Okay, so that is e raised power I squared all over 2I. And then that is e raised power I squared is minus 1. So e raised power minus 1 all over 2I. So in essence, we are saying that the residue f comma I is e raised power minus 1 all over 2I. Or if you like, that's 1 over 2ei, like that, because e can come down. So that's what we have there. 2ei. Um, so we can then do the integration. Therefore, integral from minus infinity to infinity of e raised power ix all over x squared plus 1 dx will simply be 2 pi I multiplied by the residue f of I, or all the residues within the pole. So 2 pi within the contour rather, 2 pi I times 1 over 2 e I. 2 e I. So 2I cancels 2I. So we have pi over e. And if you like, that's pi e raised by minus 1. And that is exactly what the result is, like that. So that's the result right there. So pi e raised by minus 1. So, and pi e raised by minus 1, by the way, if you try it numerically, you get 1.15, blah, blah, blah. So in case you're not sure how that is, it's only real. The imaginary part is there. That's why you have 0.0 here. So what do we do? So pi e raised by minus 1. So this is pi. Oh, okay, I already have that there. Pi times e raised by minus 1. So if you check that out, you get 1.155, blah, blah, blah. So we have 1.153. So 1.15 to 2 decimal places is correct. So that's what that exactly is. And this is not okay, yeah, this is what we have here in short. Then we move on to example 3. For example 3 now, we have integral from minus infinity to infinity of cos x over x squared plus 1 dx. So if you use the identity, cos x is actually the real number part of e raised power ix. Normally e raised power ix is actually cos x plus I sine x. So if you have cos x here now, we simply have the real part of e raised power ix. So just like what we did before. So this whole thing now is just the integral. So this is exactly the same expression like before. So whatever you get here, if you now get a an imaginary part of this, you rest it, and then so this expression is fundamentally the same thing as pi e minus 1 that we got before, basically. So, and that's so don't anytime it's half cost like this, you want to relate it to e raised power ix to make life easy for yourself, for sure. So that's how that goes. So we have that result. So you can see it looks really tricky, but since you've solved a problem like this before, and cos x is the real part of e raised power ix, you can just use your e raised power ix here, and then If at the end of the day you end up getting imaginary and real parts, rest the imaginary part and focus on the real, which happens to be fundamentally the same thing like what we got before. So example 4, which is a bit more advanced. Here you have to evaluate integral from 0 to infinity of x raised power a minus 1 all over 1 plus x dx, where a lies between 0 and 1. So you can use a keyhole contour where I is actually pi over sine pi a. So in this case now, if you use it, I mean, this is just a jump now. So we end up evaluating this to be pi over sine pi a. So the standard results for this kind of thing. So standard result generally for real integrals via complex method. Integral from minus infinity to infinity of dx over x squared plus a squared is pi over a. That's why when we did x squared plus 1, we just got pi, that's pi over 1. If it is x squared plus 4, we get pi over 2, and so on and so forth. Then when you have cos ax over x squared plus b squared, you get pi over b e raised power minus ab, right? Then for integral from minus infinity to infinity of sine x over x, you end up getting just pi. These are some standard results we get in that situation. So in summary, complex methods allow evaluation of difficult real integrals by extending into the complex plane using contour integration and applying the residue theorem. And the key steps involve to identifying poles, computing residues, and choosing correct contour. So these techniques are widely used in physics, engineering, and applied mathematics. And since we are talking about applications of complex numbers, you're going to still see the applications of these things in things like differential equations, physics, and engineering in general. So just watch out for that. So we come to that point where we have some practice problems to play with. So let's flash them in fives. 1 to 5, you have 1 to 5 here. Uh, of course, from what we know already, we know the answer, the final answer of this is going to be pi over 2. The final answer of this will be pi over 3. The final answer of this, I'm not sure because there's now x squared here, so you want to try that out. Maybe I don't know which. I'm going to solve two problems. I'll tell you very soon. So 1 to 5, 6 to, okay, I can show 6 to 11, and then 12 to 17, 12 to 17, and lastly, I have the rest of them. Okay, so I'm solving two of these problems. So solving two of them, I'm solving 3 and 10. Question 3 is x squared all over x raised power 4. Yeah, thankfully I'm solving that because it's looking really complicated. Then I'm solving 10. 10 is, what does 10 look like? Okay, 10 also has x squared plus 1 raised power 2, like that. So let's go on and deal with these two problems as we begin to bring this home gradually. Okay, let's go for problem 10. Oh, sorry, problem 3, first of all. Problem 3. So we want evaluate to evaluate I, which is the integral from minus infinity to infinity for x squared all over x raised power 4 plus 1 dx. So what do? We take the steps. So step 1. Step 1, we find the symmetry. Find symmetry here. We are dealing with minus infinity to infinity. So here we have the integrand. So we see that the integrand is even. The integrand is even. So we can say that I is equal to 2 integral from 0 to infinity. Minus infinity to infinity, we can break it into minus infinity to 0 and 0 to infinity. So that's not like 2 of 0 to infinity, and that's x squared all over x. And we have integral of x squared over x raised to power 4. That's integral of x squared all over x raised to power 4 plus 1 dx, like that. So, and then we go for step 2. In step 2 now, we use known results. We use known results. So the known result is that integral, okay, we say the standard, or better still, a standard contour a standard contour integration, a standard contour integration results gives integral from 0 to infinity of x squared over x raised to power 4 plus 1 dx. And that will be, so normally we know this x raised to power 4 plus 1 should give us like it should give us pi over 2. But then we have the additional part, which is 1 over root 2 in addition, and that will be pi over 2 root 2, of course, which uh we can then we can rationalize. That's pi over 2 root 2 times root 2 over root 2. That's like multiplying by 1. So we have pi root 2 all over, yeah, this is pi over 2 root 2, right? I think, what do we need to do here? Okay. Yeah, I think I'm getting ahead of myself. So that is pi over 2 root 2, from what we have there. So with that in place, then we can go for step 3, which talks about the final answer. Step 3, where we have the final answer. Final answer. So that is this expression is what we got already. So that tells us that I now is equal to 2 times pi over 2 root 2. Okay, so this 2 cancels this 2. So I is equal to pi over root 2. So we can then rationalize that. So I is equal to pi over root 2 times root 2 over root 2. So that means we have I to be pi. Not necessarily, that's just pi root 2 over 2. Yeah, we can have it this, we can leave it here, can leave it this way, or we can rationalize and bring it this way. So that's what we get as a final answer for problem 3. And that takes us to problem 10. Problem 10. So for problem 10 now, so we need to evaluate I equals integral from minus infinity to infinity dx all over x squared plus 1 squared, like that. So first step, we have step 1. Step 1, make it a complex. Before before I even go with this, I'm trying to think. I'm trying to think what I want to do with this now. Okay, this one will be 4. Uh, okay, let me just leave it alone. Trying to think, trying to think of doing that one, and we're going to get like 4 poles there. I think x raised to power 4. We should get 4 poles. Yeah, but that's fine. Let me just go on with this. So, the complex function. So complex function here would mean f of z equals, we have 1 over x squared plus 1 all squared. So that'll be 1 over z squared plus 1 all squared, first of all. And then, of course, the functional part is this expression here, z squared plus 1. So from z squared plus 1, uh, which can be done as z minus I into z plus I, we have we have two poles. We have two poles, z equals I and z equals minus I. So we have those two poles. So, but then what do we do? However, we use the upper half plane, that's the positive one, the upper half plane, which implies pole at z equals 1, and it is of order 2. So the pole at z equals 1 of order 2. So we then move on to step 3. Or is this still step 2? Step 2, we have residue at second order pole. So what does that look like? So for a pole of order 2, the residue of the function at I now is limit as it approaches I, d dz, because it's a second order thing now, so we now need to apply the general residue theorem. d dz of z minus I all squared multiplied by f of z, like that. So that means we have limit as z approaches I, d dz of, so this is z minus I all squared, because normally here, so this is z minus I because of the squared, right? And then we have f of z itself is 1 over z squared. That should be z minus I squared, z plus I squared, because z squared, z squared plus 1 is z minus I, z plus I, but everything is squared again. That's why each of them will carry a square. That's why we're even multiplying this by square like that. So this cancels this in essence. So we have, so what I'm saying is that, in case that's confusing, what I'm basically saying is that this expression, we have z squared plus 1 all squared. So that is z squared plus 1. Normally, when we factorize, that's z minus I, z plus I. We've done that a lot, this alone, but everything is now squared. So we have z minus I squared, z plus I squared. So because this is what we got, we got our 1 from. So we'll multiply by this at that point again. So that's what we have. So z minus I squared cancels z minus I squared. And then we move on to have the limit as z approaches 1, I rather, for d dz into, we now have 1 over z plus I all squared. We need to differentiate this. So that's what we get. So we need to do the differentiation. So to differentiate that, right, we still have limits as z approaches I, to differentiate this, we can say d dz into z plus I, all raised by minus 2. Okay, that makes life easy for me usually. So we have limits as z approaches I. So to differentiate this now, generally speaking, bring down the power, that's minus 2. Then after bringing down the power, differentiate inside, differentiate z, that you get 1. Then the original thing, you have z plus I, reduce the power by 1, that's minus 3. So that is us differentiating. So that's limits as z approaches I for minus 2 over z plus I raised power 3, like that. So we can then substitute I for 3 now, z for I for z. So that's minus 2 over I plus another I raised power 3. So that is equal to minus 2 all over minus 2 over 2I raised power 3. So we are still doing the residue, don't forget. Though we are a lot, if we are far gone, but that's the residue of f at I. That is now minus 2 over 8I cube, and then that is minus 2 over 8 times I. So that's like I squared times I now. So of course, this is 2 here is 1, 2 here is 4. So we have minus 1 over 4. Then I squared is minus 1. Then I down there. So that is minus and minus will cancel. So it's like we have minus into minus 1 over 4I. So still the residue. So that's residue of the function at I. So that is simply 1 over 4I. Okay, so we got the residue, so we can go back to where we started from. Uh, Step 3 now, we now apply residue theorem. Apply residue theorem. So to apply residue theorem, it means that I now, which is, what's the original expression again? Let me see. Yeah, integral from minus infinity to infinity of dx all over x squared plus 1 raised to power 2 is equal to 2 pi I times the sum of the residues. So that is 2 pi I times 1 over 4I. 1 over 4I. So I cancels I. 2 here is 1. 2 here is 2. So that is equal to pi over 2 at the end of the day. So uh, overall, overall, we have that I, which is integral along the closed path for um from minus infinity to infinity, right, of dx all over x squared plus 1 squared is equal to pi over 2. So this is more like the same thing like if we had had x squared plus 4, like that. So that's what we get. So with that, we come to the end of this interesting video talking about um, real integrals via complex methods. Don't forget to try your hands on all the 20 questions. I've done two already. So 1 to 5, 6 to 10, or rather 6 to 11, then 12 to 17, 12 to 17, and we have the rest. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, why not go ahead and subscribe right away? Hit the notification bell also so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like having seeing some videos first before others see them, and also seeing some videos exclusively that others don't get to see because we are special as a member of the channel. You can request for PDF copies of my notes for your personal use. You can always you can also hang out with me online or physically if you're in the same geographical location to discuss whatever interests you on my channel, be it maths, data related stuff, scholarships, writing books, anything at all. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.